Hi, welcome to our 1:30 press conference, new results from inside the ozone hole. We have Ann Douglas, Aurora Project Scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Natalya Kramarova, the Atmospheric Scientist at Goddard. And Susan Strawn, an Atmospheric Scientist also at Goddard. Thanks.
Good afternoon. It's my pleasure to introduce to you some of the research that's going to be discussed by my colleagues, Natalya and Susan. The ozone hole, which we have pictured here, has been for quite some time a regular feature in the Antarctic spring. I'm sorry. I just saw more text than I wrote, and I thought, what am I looking at? Now I get it. Wasn't understanding the projector. Okay, so these are some pictures since the launch of Aura, which was in July of 2004, that show the ozone hole each year. And when you look at them, you do notice, you think, well, it is a regular feature. But the other thing that you would notice if you look carefully is that there's quite a bit of variability from year to year. And especially if you look in 2012 and you're looking critically, you're noticing, well, it's a lot smaller that year. Now, we know that the chlorofluorocarbons that were banned by the Montreal Protocol and its amendments have been decreasing in the surface. And we know that the stratospheric gases that are produced when the chlorofluorocarbons are broken apart in the stratosphere, like hydrochloric acid, these are decreasing. And the big question that everyone is looking for is evidence that the stratospheric ozone is starting to increase due to the chlorine decrease. And scientists are asking you, is the stratospheric ozone hole recovering? And what we want to talk about specifically is just a couple of these years. We want to talk about 2012, which was a much smaller ozone hole than any prior year, except 2002, any prior year that you're looking at here. It's the second smallest ever. We want to say, well, why is that one smaller? And then we would also notice 2006 is the largest ozone hole ever, which you're seeing here on this record, and then 2011 was almost as large as 2006. So, it's perhaps surprising to see the second smallest ozone hole the year following one of the largest. And what we're going to do is explain to you why this is happening. The bottom line of what we want to show you is that in terms of whether the ozone hole is recovering or not, we're not there yet. And that's what Susan and Natalya are going to tell you more about. So we have a legacy of metrics from space. This timeline is showing you how long we've been measuring total column ozone in the stratosphere, or from space, total column ozone. It started with Nimbus 7 TOMS that was launched in 1978, and then followed by a succession of TOMS instruments, and then more recently, the OMI instrument, which is on Aura. And that was launched, as I said, in July of 2004, and then the SUMI MPP, the OMS instrument on SUMI MPP, which was launched in 2011. And both of those missions are still continuing. And from this long record of total ozone observations, scientists have developed some metrics which we consider to be classic, and these are the ones that people talk about the most, that are used to describe the ozone hole each year, and place each year in the context of the previous years. So the drawing is just a picture to remind you that the total column measurement is measuring all the ozone from the surface to the top of the atmosphere, with most of the ozone there in the stratosphere, where it says ozone layer greatest thickness. So when we're looking at the total column, we're looking at everything from the surface to the top. And the drawing shows you what one of the classic metrics is. It's the ozone hole area. And that's the area in the Antarctic with a total column ozone below 220 Dobson units. And that's the area shown by the white circle. Another common classic metric is the minimum amount of ozone that is measured in any year. What was the smallest value that we got to during any year? And the limitation to these is that there's no information in the vertical, so you don't necessarily really understand completely what's happening. You're just looking like at a flat table. And when you can look at the profiles, you can see a lot more. So we have some new metrics that have been derived from instruments that look right inside the ozone hole, and then they let us figure out what the processes are in the column, and then by accounting for those processes, we are able to tell what's happening and what's really controlling the size of the ozone hole between one year and the other. And we're going to be looking at some data from the microwave limb sounder, which is one of the instruments on AURA. And there's a picture of AURA. And we're going to be also looking at profiles from the Ozone Mapping Profiler Suite, which is on the SUMI NPP. And addressing directly two questions: why is the 2012 ozone hole the second smallest since the late 1980s? And why do the column measurements in 2011 and 2006 appear the same? Natalya.
Well, as a result of the Montreal Protocol, ozone-depleting substances are declining. Because of this decline, the Antarctic ozone hole is expected to recover. Thus, scientists and public wonder, is the Antarctic ozone hole recovering yet? To answer this question, let us to examine measurements, starting with one of the classic ozone hole metrics, the Antarctic area with a total ozone amount below 220 Dobson units. This figure shows you the area of the Antarctic ozone hole over the past 34 years, which were derived from total ozone measurements. And the gray line on this plot shows the estimated level of ozone-depleting substances in the lower Antarctic stratosphere. The area of the seasonal ozone hole depends on the level of ozone-depleting substances and the temperature at the edge of the ozone hole. In early ages, the area of the Antarctic ozone hole rapidly increased because of fast growth of ozone-depleting substances. Since mid-90s, the area of the Antarctic ozone hole stopped growing, even though the level of ozone-depleting substances continued to grow until around 2000. This was because in early 90s, the level of ozone-depleting substances eventually reached the level necessary to destroy almost 100% of ozone in low Antarctic stratosphere. So any additional growth of ozone-depleting substances could not make the ozone hole any larger. After reaching saturation in early 90s, the area of the Antarctic ozone hole has been mostly controlled by the year-to-year temperature variability. In addition, the changes in the year-to-year changes in stratospheric meteorology also affect the area of the Antarctic ozone hole. Last year, in 2012, the Antarctic ozone hole was the second smallest since early 90s. And this was caused by unusual meteorological conditions, not because of reduction of ozone-depleting substances, as the level of ozone-depleting substances is still much higher than in early 90s. Currently, small declines in levels of ozone-depleting substances are far too small to show the ozone recovery in comparisons with year-to-year variability. Future projections of lower levels of ozone-depleting substances lead to a prediction of the time when the ozone hole will be fully recovered. The blue line shows the model area feed, and the gray shaded area indicate uncertainties that arise from uncertainties in estimating temperature and ozone-depleting substances. The model predicts that the ozone hole will be fully recovered between 2058 and 2090, most likely in 2070. The ozone recovery should become apparent in about 2025. So now let us look at last year's ozone hole, which was the second smallest in recent years, and explain why it happened. So now let's ask to consider evolution, seasonal evolution of the 2012 ozone hole. This slide shows two classic ozone hole metrics that are derived from more than 30 years of total ozone observations. These metrics are daily ozone hole area, and the minimum ozone concentration over Antarctica. The white lines show the mean values, and the gray shaded area indicate the range where the most measurements fall. The black thin lines show the minimum and maximum minimum and maximum values. The red lines show the values for 2012 that were observed with the new ozone mapping and profiler suite. This instrumental suite was designed to measure total and vertical ozone distribution and was launched on the board of Suomi National Polar Orbiting Partnership satellite in October 2011. In the beginning, in August-September, the 2012 ozone hole developed with the same rate as in previous years, which indicates that the level of ozone-depleting substances are still high enough to cause severe ozone depletion. Something unusual happened in October-November time period. Both metrics indicate that the ozone hole diminished earlier this year than in previous years. New OMS allows us to look inside the ozone hole and study vertical ozone distribution inside the ozone hole. We trace the center of the ozone hole and using total ozone measurements shown on the top plot. And the vertical ozone distribution is shown on the bottom plot. You can see that severe ozone depletion was observed below about 20 to 24 kilometers, starting from the mid-September and lasting almost by the end of November. The minimum total ozone concentration was observed by about October 1st, while the minimum concentration in the lower Antarctic stratosphere was observed by 10 days later, in the middle of October. The ozone build-up at higher altitudes, which was caused by unusual meteorological processes, masked the severe photochemical loss in the lower stratosphere and caused the total ozone to increase, which created a false impression that the Antarctic hole could be improving as a result of the Montreal Protocol. In conclusion, I would like to say that the Antarctic ozone hole is not growing and is expected to recover by the year 2017. But currently, we do not see that the Antarctic ozone hole is recovering. Our work demonstrates that the classic ozone hole metrics that are based on total ozone observations have limitations. They don't tell us the whole story. Ozone increase in higher altitudes caused by meteorological processes can mask severe photochemical loss in the lower Antarctic and create a false impression that the Antarctic ozone hole could be improving as a result of the Montreal Protocol. The ozone recovery should become apparent in next decade, but we are not there yet. And with that, I would like to introduce our next speaker, Susan Strong.
Good afternoon. Scientists expect that the Antarctic ozone hole will begin to improve in coming decades because the Montreal Protocol has led to decreasing levels of atmospheric chlorine. The findings I'll show today are on unexpected variability in polar meteorology that also affect the severity of the ozone hole. So I'd like to show you the ozone holes of 2006 and 2011. They're shown here. This is data from the Microwave Limb Sounder, or MLS instrument on the AURA satellite. This is stratospheric column ozone in early October. Both of these ozone holes were very similar, and they were two of the largest and deepest ozone holes of the past decade. The white area, the white circle on those plots shows where the ozone hole is. But if we look inside the ozone hole on a level where the ozone depletion is occurring, and we look at some of the other chemical species, we see they differ in these 2 years. So we wondered, why are they different when the ozone holes themselves look so similar? So to get a little more information, we're taking a look at nitrous oxide, or N2O, which is also measured by the MLS instrument. And that's what's shown in the lower two figures on the screen. 2011, which is on the right, shows much higher levels of nitrous oxide than we're seeing in 2006. Now, nitrous oxide isn't involved in any ozone depletion reactions, but it does give us some insight into the chemistry that's going on in these years. Nitrous oxide tells us about the journey that an air mass takes as it travels through the stratosphere on its way to the Antarctic. In fact, what we use it to tell us about is chlorine, or inorganic chlorine, also called CLY, which is found inside the ozone hole. Inorganic chlorine is important, and what it represents here is all the chlorine that's available to participate in ozone depletion reactions. Now, chlorine affects how much ozone depletion occurs, but we don't actually have direct measurement of all the inorganic chlorine, but we know a lot about the relationship between nitrous oxide and chlorine, and so that's how we'll figure out what's going on with chlorine. That's what's shown in the top panel here. Nitrous oxide and the chlorofluorocarbons are both emitted at the surface, and as they rise into the stratosphere, as they go higher and higher, UV radiation from the sun breaks them down. So when you go up in altitude, as the CFCs break down and decrease in abundance, the chlorine that comes off of the CFCs increases. So when nitrous oxide is low, chlorine is high, and vice versa. And we know from extensive observations in the stratosphere exactly what the relationship is between nitrous oxide and chlorine. That's shown by the black line on this figure. This comes from a paper by Schaffler et al. 10 years ago, where they measured nitrous oxide and the various chlorine-containing species in the lower stratosphere. So what we were able to do in the study is take the MLS nitrous oxide measurements and find out what their value was inside the ozone hole and look at that for the past 10 years that MLS has been collecting data. And then we could infer how much chlorine was there from the MLS nitrous oxide observations. Those results are shown as the red boxes there. And what we found was actually very surprising. Now, we expect, because of the Montreal Protocol, that chlorine is gradually declining in the stratosphere, and what we expect over this past decade was about a 5% decrease in chlorine. But what we actually found out is that chlorine is varying up and down by as much as 5% a year. So although it's gradually declining, it's a bumpy road down. So some years it's higher, some years it's lower. Now, the 2 years where I've shown you the very similar ozone holes, these are the results for those 2 years. So in 2011, we saw high nitrous oxide. That means there was less chlorine. But if there was so much less chlorine, and chlorine is responsible for ozone depletion, then we still have our mystery. Why was the ozone hole so big that year? So to answer what made them really different, we use a model that realistically simulates the chemistry and the meteorology of the stratosphere. And we ran simulations with all the full chemistry, complete chemistry involving the ozone-depleting reactions. But then we ran a second set of simulations where we turned off the ozone-depleting reactions. And that tells us how much ozone would have been in the Antarctic had there been no depletion at all. And when we turn those off, we see in 2011, those purple colors in the middle represent very low ozone. So 2011 would have had less ozone even in the absence of depletion. And this is a meteorological effect. This has nothing to do with chemistry. Another thing we can do with the model results that's very helpful is we can look at the difference between the simulations with the full chemistry and with the chemical reactions turned off to estimate how much ozone depletion took place in these 2 years. And that's what's shown in these next two panels. On the left is the ozone depletion in 2006, and those colors indicate much higher levels of ozone depletion than 2011. About 20% more depletion than 2011. So here's the answer to the mystery. Why was ozone so low? Well, in 2011, we had less ozone depletion, but we also know that less ozone was there in the Antarctic to begin with. What I should have mentioned before is this meteorological difference, that the fact that it was lower in 2011. This is part of the normal stratospheric variation or circulation. Ozone is produced in the tropics, not in the polar region, but it's transported by the winds from the tropics to the polar region. And so that varies a little bit year to year. And so what this is telling us that in 2011, the wind simply blew less ozone to the Antarctic. So that's really the reason why the ozone hole appeared so severe in 2011. There was less ozone to begin with, less ozone depletion. We ended up in the same place. So the interesting result we have here is that chemical loss can actually vary quite a bit from year to year without any obvious impact on the total column. And that's the quantity we often use to say how severe the ozone hole is. And the reason it doesn't show up in the total column is that the winds bringing ozone to the Antarctic are also varying each year. So it covers it up. And this shows why it's so important to be able to look inside the ozone hole at levels where the ozone depletion is occurring. The column metrics just don't give us the whole story. So I'd like to now stop and sort of summarize what we learned in these two studies. we've shown how the three-dimensional data from MLS and the OMPS instrument give us greater understanding of what's going on inside the ozone hole and what's causing it to vary each year. Now, we've known for a long time that chlorine and temperature are the key things that control how deep the ozone hole is and how large it is. But our two studies today also show that what also matters are the winds that carry ozone to the Antarctic at and above the levels where the ozone depletion is occurring. And that's affecting the ozone column too. So they can affect how severe or not severe the ozone hole appears to be. In 2012, Natalya showed us that there was severe ozone depletion in the lower part of the Antarctic stratosphere, while above winds brought in more ozone. So the net result was a smaller than usual looking ozone hole. But then in 2011, we saw the winds play the opposite role, where the winds brought less ozone to the Antarctic than usual, and there was less ozone depletion. But the net result was an ozone hole that looked just as big as some of the biggest holes of the past decade, including the largest one observed, 2006. So these classic ozone metrics just don't get under the hood of the ozone hole. You really need to see inside at different levels in order to understand what's going on. But finally, the thing that I think a lot of people want to know about is, when is the ozone hole going to recover? When are we going to see signs that the decreasing levels of chlorine are really having an impact on the ozone hole? And I'd like to explain what we expect to happen in the coming decades using this figure. This figure is chlorine. It's both observed chlorine for past years that has been derived from observations. It's chlorine for the Antarctic lower stratosphere. But the years that are in the future, going from the present on out to the middle of the 21st century, that's a projection of how we think chlorine will decline. Now, before the 1990s, the chlorine levels in the atmosphere were quite low, but they were rapidly increasing. And at that time, the ozone hole area varied a lot from year to year, and it varied depending on how much chlorine was there and how cold it was, and also depended on the winds. So the whole area varied a lot. But after about 1990, and as Natalya was showing, the ozone hole area didn't vary that much. It was very large almost every year, and the slight variations that we saw had to do with temperature, not to do with chlorine. And the reason for that, as she explained, was that there was so much chlorine there that just a little variation up or down didn't matter, because there was more than enough chlorine to destroy basically all the ozone in the Antarctic lower stratosphere. And that's sort of the period of time we're in right now. Since about 1990, we're in a period of very large ozone holes. The results from this study are shown in red. And so one thing we learned is that chlorine actually varies up and down quite a bit each year. But since we're above this threshold of about 2,500 parts per trillion of chlorine, we've still got so much chlorine up there that the ozone hole area just doesn't depend on chlorine. And this is why we're saying today that it's too soon to yet detect recovery of the ozone hole due to declining chlorine levels. But we think that coming very soon, in just a few years, maybe 5 years, hopefully by the end of this decade, as the chlorine levels gradually decrease, and the blue line is to show you how the chlorine levels might decrease, because now we know there's a lot of interannual variability from meteorology that makes the chlorine kind of go up or down each year. It's not going to smoothly go down. So some years we expect chlorine's going to dip back down into this low chlorine regime where the ozone hole area depends on how much chlorine is there. So we'll start to see smaller ozone holes. But then in other years, we might have a little meteorological variability that bumps us back up into the high chlorine regime. If it's a cold year, we'll still have a big fat ozone hole. So for the coming 20 years, we expect that we'll see some smaller years, some big years, but that's what we expect will happen. It's not a sign that chlorine's not going down. If we have a small hole, it's not a sign that chlorine's going down faster than we thought. We just expect some bumps on the road as the ozone hole recovers. And finally, by about the mid-2030s, chlorine is projected to be about 20% lower than it is today. By the time it's that low, we should be down into this low chlorine regime where the ozone hole area once again depends on chlorine and temperature and wind. And at that time, we expect to see consistently smaller ozone holes with full recovery probably around 2070. Thanks.
Okay, are there any questions?
Why does it take the chlorine so long to sort of dissipate since we're not adding any more?
Because the...
Oh, I'm Tia Ghosh from Live Science, sorry.
Oh, sure. the chlorofluorocarbons that are producing the chlorine that destroy ozone, they're very stable molecules that have a very long atmospheric lifetime. So they have to travel really high up into the stratosphere to get broken down. And so that slope going down is really controlled to a large extent by the circulation of the stratosphere, how quickly those CFC molecules can get up high and get broken down. And so it's really governed by stratospheric circulation.
Gabriel Popkin, Science News. So I guess my question is, does it matter as far as we're concerned where the ozone is? Natalya, you showed that in 2012, there was ozone very high up that was masking a significant depletion lower. I mean, as far as exposure, does it matter if it's up there or lower?
The severe ozone depletion usually happens in altitudes below 25 kilometers. So this is the area, this is the vertical range where we should monitor the Antarctic ozone loss. And actually, as we expect the chlorine level to decline, this area, this vertical area of severe ozone loss should become smaller and smaller. So the lines should become lower and lower in altitude. And this is when we will see that the ozone hole is recovering.
Can I add to that?
Sure.
Just to add to that, if you're talking about UV exposure at the surface, it doesn't matter to you what's there. I think what we think could matter to people would be when you see a smaller ozone hole one year, then you might think, oh, it's never coming back, we're done with it. And then the next year it could be just as big as it was a few years ago. And then people would say, what's up with that? So, so from a point of view of UV exposure, it doesn't matter what makes it fill in. But from a point of view of what's happening with the chemistry and is the Montreal Protocol really working, that's where you need to know whether the chlorine itself has decreased enough so that you have less loss.
Hi, this is Bas den Hond, Trouw and The Economist. Could you clarify the last point just a bit? I had the same question and I'm not sure we've got the answer. Is there a difference between you saying there's a large ozone hole but it's masked by ozone higher up? You might also say, okay, in that case it's not so large an ozone hole after all.
No, the net effect at the surface is the same. Is that what you're trying to ask? Or would we feel any different? No, because ozone is blocking UV for us, and it doesn't matter exactly where it is. It's the total column that's protecting us from the sun.
Do we have any questions on the phone? Anyone else have any questions here? Okay, thank you. Our next, that's our last press conference for the day, so we'll see you all tomorrow morning at 8 a.m. Oh, it's the Europa press conference tomorrow at 8 a.m. What is the actual?